Alright, in this video I'm going to solve Midterm 3 version A, all the problems, and I'll also post this PDF online as well. I'm going to solve all the problems. You can also go through the lowest graded problems. I know that some fraction of you did pretty well on the lowest graded. It's really difficult for me to just define what would be the most appropriate problem to actually consider in detail. So therefore, I'm going to consider all of them. Okay, so I'll start with one. So in the one, we have a transformer with that many turns on the primary and that many turns on the secondary. On the primary, the RMS voltage is given and the average power is given. Okay, so we need to find the RMS current on the secondary. So let's just write what we know. We know that the number of turns in the primary is given and number of turns in the secondary is given, voltage in the primary is given, and power in the primary is given. Okay, so we know a couple of facts. So the first fact, we know that the voltage the voltage ratio, okay, in the primary and the secondary is related to the ratio of the number of turns, and this we can solve for the voltage in the secondary. We'll get this equation. Okay, this equation, and this will give us the voltage in the secondary. So we are talking here, we are given the RMS voltages everywhere and the average power, and therefore we don't need to convert anything like the peak to RMS or something like that. We'll be just dealing with RMS voltages, RMS currents, and average powers here only. All right, so now what is also given here, so what we found is voltage. We need the current. What we are additionally given is the power in the primary. We use the following fact that our transformers are 100% efficient, so that this is what you usually assume about them, so the power in the secondary equals to the power in the primary. Okay, so power in the secondary equals to power in the primary, but we also know that the voltage in the secondary times the current in the secondary is the same as the power in the secondary, right? So this is the definition of the voltage. Okay, so we found the voltage in the secondary. Over here, the power in the primary, we know we can solve for the current. Right, so here we go, we solve that. So we solve that equation for the current, substituted the voltage. Okay, substitute the voltage. After substitute the numbers. Okay, so when I substitute the voltage, I did this mathematical manipulation, right? So when I divide by the ratio, I have to remember that it will be a flipped ratio, so it's in P divided by NS. Okay, so when substituting the numbers, I got the final result. So, yeah, please make sure you understand the problem like this. Okay, so there is another problem over here. So actually, I also gave it to a neural network. It's kind of interesting. It's kind of solved that, not really correctly, but the way it failed is pretty interesting. Anyway, so it was quite eliminating. Anyway, so what we have here, we have some light source at the bottom of the pool. Okay, this light, and the pool water is still. Okay, so this light source emits light, of course, everywhere, right? Emits lights, of course, everywhere. So I'm showing it over here, but at some angle, okay, the light will be completely reflected back into the water. So the angle at which it happens is called the critical angle. Okay, and we know how to find this because it's given by the ratio of the refraction index for the low refractive material. So in this case, air, to the higher refraction index, in this case water, so it's 1 divided by 1/3, and then we can solve this for that angle. We can find this angle. It will be a number. Okay, you can compute this number, so you will find this angle. Okay, this angle. This is not what we need to find. We need to find this radius over here, or this distance. So this is the normal, right? So this is the source. So this distance is the same as this distance. Okay, this distance is the same as this distance, so we need to find this r. So what's given, the h, the depth of that pool is given. Okay, h is given. We need to find r. We know this angle. Okay. Well, very good. Very good. So what do we do next? Well, we know that the tangent of this angle, tangent of theta c, okay, tangent of theta c, is given by the ratio of the opposite side to the adjacent side. Okay, that's adjacent side, that's opposite side. Again, tangent of theta c is given by the opposite side divided by adjacent side. Well, adjacent side we know, right? It's the same as h. So from that, and theta c we found already its number, remember that. So what we need to do, we need to solve this for the radius, okay, for r, and r will be h times tangent of theta. We can just substitute the numbers we obtained and what we know about h, right? So, and get the final result, and then cross-check it with our key. Okay, number 3, I will give you a chance to read this one. All right, so in number 3, what we are given this circuit. So we closed the switch and we waited forever. We wait for some time until the current reaches its steady value. When the current actually reaches its steady value, it means that the inductor would not affect anything. The constant current, right? Inductor does not has any potential difference, can be replaced with just a straight piece of wire. Again, this is for the steady current. Okay, the potential difference in the inductor is proportional to the change of the current, right? So once the current is steady, there is no potential difference across the inductor. And then we can forget about it. Okay, we can find the current, and the current will be just given by the EMF, the potential difference, divided by the resistance of this circuit. Okay, so that's the current. And then we have to remember that the energy stored in the inductor is given by the inductance times the current squared divided by 2. Okay, and then we just substitute what you found about the current and compute. Okay, everything is given. L is given over here. Remember that we have to write this in the SI units. Okay, so epsilon is given over here, and R is here. Okay, so now we'll consider number 4. Okay, in number 4, I can immediately get rid of these ones. So this is application of the Snell's law. I know that these angles, so that this angle, and this angle, so this angle, these slopes of these curves is same as, actually, as a matter of fact, as well, let's just draw the normal. This angle and this angle is the same as this angle. That's the property we actually derived independent of the so this is, say, air and air, this is an air, and this is n of this glass. Okay, doesn't matter if it's red and violet. We define this property using the Snell's law that these slopes of all these 3 curves has to be the same. Okay, so and therefore it's only these 2 possibilities which are possible, and now you have to remember that for lower, for red light, okay, for the and also infrared and others, or in violet and ultraviolet will be on that side. So, but the red light is refracted less. What does it mean that it refracted less? That when it goes into the material with higher refraction index, that this angle will be larger. Okay, so, and then the answer will be 1. Okay, the red light is refracted less. This is also indicated by the fact that the refraction index for the red light is less than the refraction index for the blue light or violet light. Okay, number 5. I will give you a chance to read this problem. Okay, so what we are given here, we are given 2 currents. Okay, very good. So do they current repel or attract each other? This is the question the first question we need to answer. Well, let's look at this current over here. Just let's compute the magnetic field which would be created below this current. direction of this magnetic field? Well, this will be the direction of this magnetic field. Use the right hand rule, right? So we point our thumb in the direction of the magnetic field and we curl our fingers of the right hand, right? And this will define the magnetic field, so it will go like around that loop over here. So it will be pointing out the page on this side of the current. Here it will be pointing in. The magnetic field generated by the wire 1. I will call it B1 over here. So now using this B1, I can also remember what would be the force, the direction of the force acting on the current, okay, in this magnetic field. How do I do this? I direct my arm in the direction of the current, then I curl my fingers, I bend my fingers in the direction of the magnetic field, and my thumb will point, it will point in this direction, which is negative y direction. So whatever I get, it has to have negative y direction, this or that. Okay, now I need to compute the actual number. I have to remember that the magnetic field force between these two wires will be, so here the currents repel each other, right? So the magnetic force is given by this equation. So this is mu0 times I1 times I2 divided by 2 pi r, where r is the distance between these two wires. I need to just substitute the numbers which are given over here. I need to remember the use SI units for the distance, and I will get the result. Please compute, check, and see. Number 6, I will let you